Oh, this is loud. All right, hello everybody. I hope you guys are hanging on to consciousness out there. We're almost done with the day. My name is Michael Miller. Also, shout out to my co-author Brandon Campbell, who isn't here today. I work for Northrop Grumman, which is one of the largest aerospace and defense companies in the United States. And then specifically within Northrop Grumman, our team is Digital Innovation Systems. We're a really small team, and we're actually based out of Roy, Utah, which is a North Salt Lake suburb. So that's where we're coming from. This whole presentation is geared towards Northrop's use case, which is very much engineering, manufacturing. All right, so this is a quick overview of what we're going to talk about. Basically, the takeaway here is it's going to start out really theoretical, high level. I'm going to make lots of promises. And then we're basically going to go more and more like actual real world use cases as the presentation goes on. So bear with me. It's not all just fluff, I promise. All right, so let's start out with, zoomed way out, big picture. In engineering, in any engineering application, being able to really communicate exactly what you mean is incredibly important. It can make the difference between a successful and a failed program. It can make the difference between a happy and a dissatisfied customer. Based on your use case, it can impact safety of people or even national security. So, communication, that's 100% key. That's what we care about. Now, in the defense industry, but really, any engineering domain, you have tons and tons of natural language. Every program that ever exists is generating gigabytes of data. And it's not just while you're designing or after you're done, it's the whole program lifecycle. From the minute you get the proposal, that's a document, you're writing your response, you're writing your requirements and your specs and your design documentation, all the way until you're done. Maintenance documentation, legacy, like instruction manuals, all of this is written down. There's so much data in here. And this is not, light bedtime reading. This is rich technical content. It's expressing, very specific details about very specific things. And historically and today, it's tough to work with this large amount of data. Really today, if you want your engineer to know what is in an old maintenance document, your best bet is just to have them sit down and read it. There's no workaround that exists yet. Maybe we'll get there someday. So yeah, this is a tough problem. We have all this information. We want to use the information, but it's tough to get to. It takes a long time, a lot of effort. Knowledge graphs, I'm going to call them conventional knowledge graphs from now on, are touted as a solution to this problem. So we can take this huge store of data, we can pop it into a knowledge graph, and suddenly I don't have to read it because my computer can interact with it in this nice format. That works. But it's a lot of effort to make knowledge graphs. We've had several presentations today about how to do that. It's like an ongoing research field. But then more importantly, they're rigid and they often fail to capture specific nuances in the engineering documentation. And I'll get into that later. So what are we going to do about it? This presentation is about discourse graphs. It's a proposed solution. It's a new type of knowledge graph. It's fundamentally different from like all the other knowledge graphs that you've heard about today. It is natural language modeled as a graph. So not an interpretation of natural language or just specific pieces removed out. It's natural language as a graph. It captures all information. Every word that was in the initial text is in the knowledge graph at the end. And you can make discourse graphs without having to have a large trained model, so you don't need a training data set. We believe this revolutionizes knowledge mobilizations, and it can be used kind of across the program lifecycle, all the way from the beginning through a request for proposal shredding until years after the program is done, mining knowledge and integration of maintainer documents. All right, so that's the promise. Let's make it real here. So some background. Remember, we're starting theoretical here. All right, I've got some natural language for us. This is Alice in Wonderland, and I am going to read it to you because we're going to talk about it a lot, but I'll be quick. All right. She was a little startled by seeing the Cheshire Cat sitting on the bough of a tree a few yards off. The cat only grinned when it saw Alice. It looked good-natured, she thought. Still, it had very long claws and a great many teeth, so she felt that it ought to be treated with respect. So there's some natural language. It's not an engineering document, but it's gonna work for us today. All right, so let's talk about this natural language. Here's some basic, kind of entity extraction that I have manually done. And I want to know, hey, what are we talking about? Well, I've highlighted every mention of Alice in orange and the Cheshire Cat in blue. That's what we're talking about. This is basically just natural language basics. But for us as humans, we can read this, no problem. I can pull out the information. But you can see that, like, from a computer's perspective, it's not very organized. We kind of go back and forth between what we're talking about with the references. Definitely nonlinear. And this is, and so then we can ask, I talked about what's in the document. Now I can say, what do we know about those topics? So, okay, what do we know about the cat? Well, he's got long claws, it said so, he has a lot of teeth. Alice feels that he ought to be treated with respect. So, this is some information that I pulled out. Again, easy for me to do, easy for a child to do, really hard for a computer to do. All right, so now I'm gonna pause and quickly say that, yes, the path of natural language, there are many, many large language models which are specifically implemented to do this kind of task on linear language in its natural form. I'm not gonna talk about those very much. It used to be BERT, now it's ChatGPT, but it's another large transformer and we're gonna see them keep getting better. But yeah, those approaches, you normally need a huge amount of training data to create those models. And then when you're talking about a specific engineering application, a lot of times the things that you care the most about don't exist yet in the world. So there is no training data. ChatGPT has no idea what my new component of my new system is called, because no one has any idea what it's called because it's never been created yet. So these models tend to not work well unless you have enough data to train them or at least fine tune them, and that's not always available. That's besides, you can't put your proprietary design documents, like send them off through the internet. So I'll set that aside. This is definitely like a sore point if someone wants to be like, why aren't we just using BERT or ChatGPT? Come talk to me afterwards at the reception when we can have beers. But for now, we're just setting it aside. All right. So we have another solution though, which normally I have to explain really well to people, but you guys already know and love knowledge graphs. So great, we have knowledge graphs. But there's some downsides to knowledge graphs. And again, I'm saying the conventional knowledge graphs. So one downside is that they're hard to make, kind of state of the art, usually is still human in the loop. Like, we can come up with systems to spit out relations and information extraction from natural language. We just had a talk about it. But normally for like Wikidata or DBpedia or whatever, you still have someone reviewing stuff, or you can crowdsource it. Like, there's lots of optimizations, but it still takes a long time. So that's one downside. The other downside, which I think is the most important, is that knowledge graphs are very brittle. So if you look up Cheshire Cat on, I think this is now Google Knowledge Graph, it will tell you that, hey, the Cheshire Cat is an instance of anthropomorphic cat. That's a pretty specific category, but Google Knowledge Graph knows about it. It will tell you what species it is. I didn't know what species the Cheshire Cat was, but Google Knowledge Graph knows. Yeah, so it's, these are pretty specific categories, but we still are missing, should the Cheshire Cat be treated with respect? Google Knowledge Graph has no idea. In Alice's opinion, what was the demeanor of the cat? Google Knowledge Graph has no idea. This information is way too fine-grained to stick into Google Knowledge Graph. If we wanted to include all that information, it would be massive, and there'd be so many relationships that it would be really hard to maintain. All right, now in this case, we don't really care very much. Lewis Carroll, he wrote that story. He picked the information he wanted to include. If I misinterpret it by swapping a verb for another one in my ontology or something like that, maybe I'll have slightly less enjoyment or something. Maybe I'll miss the moral message or whatever, but no big deal. However, remember what we said at the very beginning, precise communication is critical for engineering. I cannot swap any word. I can't, say, oh, you said this? That's pretty close to this relationship I know about. I can't make an assumption for the author. And that's kind of, the driving factor here. the author picked what words to put into this technical document. I, as the analyst or the data mobilizer or whatever I am, cannot make that decision for them. So that's the key takeaway. This is why the discourse graph as a concept exists. All right, so let's now talk about what that is. All right, so introducing the discourse graph. We've got two goals. Oh, so discourse, this is using like the linguistics definition. So a discourse is basically one or more words that has some kind of meaning. So a discourse can be a formal document, or it can just be like, hello, that's a discourse. It doesn't have to be between multiple people. That's like the conventional definition. All right, so discourse graph. So we're gonna kind of define it here. We've got two goals. The first goal is we want natural language as a graph of semantic tuples. Everyone likes semantic triples, but you can come up with ones that are just two. So semantic tuples. So it's just a knowledge graph. You know, that bullet or point one here is just we want a knowledge graph. And then we want to preserve all original data from the discourse. So this is what's new. This is what everybody else isn't doing when they're spitting out knowledge graphs and what we are trying to do. So that's the goal. How are we going to do it? There's a few options here. I'm just going to go through them. So you can do this manually. You can just take your sentence. You identify the semantic triples. So you say, here's one. You scratch out those words, put it in your graph, go through the rest of the sentence. And if you keep doing that process, you'll get a discourse graph. You'll have all the words in a graph connected however you want. So it will be a graph and it will have all the words. You did it. However, it will take you forever. It's such a pain to do it this way. Do not recommend. Another way, this is kind of like the end goal. It'd be great to train one of those large language models, and basically, there's this Penn tree bank, which is like an older data set used to create, what are they called? Not dependent constituency graphs. It's a data bank of here's a sentence, here's a graph of that sentence, or a constituency tree. Sorry, it's like a specific linguistics construct, and you just map directly. People have been training on it for years. It works great. Like the models are better than humans at constructing these things. So that's the goal. You know, we could do that with a discourse graph, just go one to the other, but you have to have a ton of training data. And like I said, I do not have that. So we've got a third option, and this is what we actually built. Turns out you can make a discourse graph by building a pipeline out of existing models with just a little bit of glue. So this is our pipeline. This is not like the pipeline. You could make whatever one you want here. But we leaned heavily on the Python module Spacey. So we've got a tokenizer to get words, part of speech tagger to get part of speech. Dependency tree parser, there's an example of a dependency tree here. You can kind of think of it like grade school diagramming if you guys had to do that in English class. But you're basically arranging words such that you can tell which words are related to which other words, which, you know, this is a great stepping stone for a graph, obviously, because a tree is just a specific type of graph. And then we have our own discourse graph parser, which basically consumes all of the information from above and constructs that data into a graph. This is like where the magic happens. It's complicated. You have to like study grammar a lot to figure this out, but you can do it. It's all rule-based currently. Like I said, if we had a big end-to-end model, it could just be AI magic. But right now it is fully rule-based. Then we use a co-reference resolver. So this is our pipeline. There's more. You know, you hook all these things together. You've got to make some design decisions here. I'm not saying that there's one true discourse graph. We had our two requirements. If you satisfy those, then, you know, all this other stuff is just design decisions, and you can optimize for your specific use case. And then you can play around with this. So you can add different layers, right? It's a knowledge graph, so additional data doesn't take away from the existing data. You can put like a semantic layer or a token layer or an entity layer. You can keep track of what parts are true or false. Like, you know, the sky's the limit. It's a graph database. You can put all your stuff. But we picked our choices for these decisions, run the pipeline, and here is a discourse graph of what we saw before, the Alice in Wonderland excerpt. We don't have to read everything on here. Does this guy have a laser? Oh, nice. Okay, but you can see we've identified cat as pretty central. And then we can kind of, if we want, we can deconstruct sentences. So we can see that cat had claws, very long claws. We see that the cat ought to be treated with respect, and we see that Alice felt that. So you can kind of see now how the initial linear natural language is now baked into this graph structure. Yeah, so that's a discourse graph and how you make it. Now let's talk about why we care. I've got 4 minutes left. All right, so this is 2 sections. There's capabilities and use cases. The capabilities are like Lego bricks, right? They're high-level things that we can do with the discourse graph that we believe we can do better than with linear natural language. The use cases are now like, let's take combinations of these capabilities and actually do something cool with it. Entity identification, you can do this with linear natural language, and a lot of the models are really good at it. But you can also now take this graph as input. You can get much better context, than just looking at the words that are adjacent to each other in a sentence. Now we can get the words that are semantically similar, or the words that are actually used together in the structure, the semantic structure of what you're trying to say. We can also just look for patterns. So this would be the equivalent of like regex in normal linear language. Now we can look for shapes in the graph. You get a lot more meaning. We were able to outperform some kind of regex-based linear language models. Topic identification. So this is another like commonly studied linguistics capability. You can also do it with a graph, and we believe that having this context is going to give you a better overall model, because you have more data that you're using as your input. And again, I'm just skimming these, but there's not too much time. Further research. So this is the fun stuff. So everything that I talked about before, you can do on linear natural language. Now we're kind of looking at stuff that you can only do if you have a graph. We have graph neural networks, which now we can plug this into, and we can do cool things like look at sentiment of either the entire discourse or specific subsections that we care about, or around specific entities that we care about for token level sentiment analysis. You can do graph-based word embeddings, link prediction. So these are all like normal graph challenges or graph problems that you apply to like biology or whatever. And now we're applying it to natural language, which is new and interesting. You can look at graph algorithms like number of connections or page rank, neighborhood identification. This is all stuff that, again, we talk about these concepts in other use cases. Now we're applying them to natural language. It'll be cool to see what we can, what results we'll have. All right, that's the capabilities. So here are some use cases. RFP shredding, request for proposal shredding. This is like the first step on a program. The customer gives you a request for proposals, and you have like some very fixed amount of time. You grab all your best engineers, you go hide in a room for 2 weeks, and you pull all-nighters, and you write your proposal, and you get it back as fast as you can. This has a lot of capabilities that we can use for this application. We can figure out what the proposal is about. We can figure out key information using our entity identification. Like maybe you want to know who the specific customer is, or what it's talking about. If you have this all in your database, we all love graph databases. Now you can look for similar proposals, and you can go get the people who worked them, or you can look for similar responses to proposals and get those engineers. The sky's the limit. You can use all sorts of stuff here. Data loss prevention. So you're a company and you have intellectual property and you have designs, and maybe you have like classified information, and you need to make sure that that isn't going where it's not supposed to go. Current approaches for data loss prevention tend to rely on more conventional models, so not ChatGPT or BERT or whatever. People are using like word search. So we can do a lot better than that with this graph approach. We can get our text into a graph. We can look for specific patterns of either illegal entities or illegal topics, and make sure that we're not losing any of that. Knowledge binding and integration. A lot of people today have talked about this, but if I have 2 documents from a long time ago, I need to figure out the specific topics, put them side by side, and I can use that to either confirm the information or maybe see if it disagrees. And maybe I can do that automatically with a cool NLP model, see if the 2 statements match. So we can use our discourse graph to help in this process. All right, so natural language, written natural language is everywhere. all over the industry. It's hard to work with, but it's really important. Discourse graphs are a unique solution. So this is a special kind of knowledge graph that allows us to do what we want to do with knowledge graphs. It allows us to mobilize data, but it allows us to do it without getting rid of any of the original data. And we see this being used, across the engineering lifecycle. And ultimately, it will result in clear communication, which is, as you said at the very beginning, is great for the engineers, for the customer, and ultimately anyone who interacts or is affected by the product. So thank you. Oh, and questions? Yeah. There we go.
How, in your example text, do you distinguish the Cheshire Cat from a Cheshire Cat?
Yeah, so I don't know if you're here last session. It's the same models, but named entity recognition and entity linking are very well-studied problems. So like the easiest way is you go and download models that have been trained on gigabytes of data to do that specific thing. So yeah, we use Spacey, and at Spacey then you can pick which model. So it's like a transformer-based model. So yeah, very sophisticated piece of code that does that, and it knows how to do it. It's a really interesting problem, but that's not one that we solved here. We just piggybacked off what everybody else had done. Yeah?
I noticed you use just text in your examples, but you mentioned a dependency parsing. Do you use actual dependency relations?
Those are used by the parser. We don't put those into the final discourse graph. The final discourse graph has a very limited set. It's hard to see it here, so you're just gonna have to take my word for it. But most of the relationships are either subject-object to indicate a semantic triple, or describes, which we insert for the special case of adjectives and adverbs, or conjugate, things like that. So these aren't, the information from the dependency graph is used to inform how we shape this graph, dependency tree, sorry. I think you've had your hand up for a while, sorry.
You showed your pipeline, and it was great, and I really like this. Is there any plan to make this open source, or somehow that we can collaboratively work on a solution like that?
I think that would be cool. That doesn't really align with Northrop Grumman's tendencies. They hold their IP pretty close. But this is now open source, and I would very much like, to see this expanded upon. We're not saying that we have the monopoly on this pipeline. All of these, or most of these, are just out there.
So the only thing where you say difficult graph parser is that's when the magic happens.
It was hard to do that too, but yeah.
That would be great.
I wish I could give you that. Yeah.
So this only works on non-items or purely text. The reason I ask is because in PDFs, sometimes you'll have other parts of information in non-text, like tables, please refer to this table for this. Is that captured in any way?
So that is totally, dependent on the pipeline.
Okay.
A lot of these are pre-baked Spacey models. So we fed it dirty data though, and turns out Spacey doesn't care about new lines. It just ignores them, which is a wild design decision for whoever came up with that. But so it'll do its best. It'll take, so let's say the table is parsed as just words next to each other with tabs in between them or something. It'll just think your sentence is very strange with the words in the table, and then it'll do its best, and it can still maybe identify some entities. You'll have a graph. It just isn't going to make very much sense. But that would be a great improvement, and one that we have always kind of pushed down the road, where basically we would want to first identify what the format of the data is, because you have natural language paragraphs, you also have tables, and then you also have diagrams or engineering drawings or whatever. And it would be great to train a model to see what's coming and then direct you based on what you have. And then we could build we wouldn't need all of this stuff to parse a table, most likely. That would be easier, but we just have to be aware of it so we're not shoving it into Spacey like everything else. Yeah?
Did you run into or manage scalability concerns with just how large these graphs would be over time?
So we use Neo4j as like our database, and we fed it hundreds and hundreds of documents, and it didn't choke. Like Neo4j is pretty good about being able to store tons and tons of nodes and relationships. It also can start getting expensive to query the discourse graph, especially with like once your entities are linked to like thousands of places. So it took a lot of optimization, but we never reached a point where we couldn't overcome it. It would always be like, oh, this is slow now, and then you'd have to go back and optimize this query or index something or however get around each problem. So no. Oh, okay. Follow up.
Yeah, it's a little bit in a different direction.
Oh, okay.
But do you think that the solution would benefit from interacting with an ontology that's like describing the domain?
Yeah, very much so. Especially with like the entity. So entity recognition tends to be important. Like it's pretty important to know what is in the specific paragraph or document or context of another entity or whatever. And having like a taxonomy of entities or an ontology of entities, that's key. We haven't done that much work there, but like I saw, for example, Pool Party, they have like a whole taxonomy builder, and I was like, oh, that would be so useful for this. So yeah, that's important. Do I have bonus time? Oh, it's going up. Oh, we can keep going, I guess. More questions?
Is it going to create the same entity that represents both?
So that's and these are all like well-studied like computational linguistics or NLP like topics. So and you will find disagreement, but typically you have like your named entity recognition, which is saying like, hey, Bank of America, that sounds like an entity. And then you have your entity linker, which says Bank of America, that's the same as BOA or whatever, and uses like a knowledge graph to link them. That's what you're describing. Co-reference is within a sentence or discourse, typically with a pronoun, not always with a pronoun. But so if you say like, I ate the apple, it tasted good, the co-reference resolver says it is referring to apple, not to I. And again, the lines are blurry. Sometimes it'll fulfill the same task, but that's like the main use case of each of those models. Yes?
I'm taking a look at this as a compression algorithm for compressing documents into a
So
format.
the way we implemented it does not compress it. It actually like explodes it in terms of data storage requirements, because you are storing every word. We're not actually, and the implementation has changed a little bit from this picture. We're now not merging entity nodes, so cat would actually still occur multiple times, and then we just put another link between them. But that's beside the point. But basically, yeah, it's not efficient. It would be interesting to see if it could be made efficient, like space-wise. Maybe it could, but yeah, that's not the challenge that we took on. But it's a good idea. Question in the back.
I wonder if last time I looked at this sort of problem, I applied then reasoning on top to do some of that compression or to sort of extract out a meaningful graph, perhaps against an ontology. Have you looked at anything like that, applying rules over the graph to shortcut?
Certainly, yeah. So this looks nice, but it's never the deliverable. Like no customer would want to see this or would know what the heck it is. So there's usually like several layers. So like entity tagging is one that I mentioned a lot. So you tag an entity, you just stick it in the graph. So now you have entities living in here also, and then you can take the taxonomy or ontology between the entities, and then you can start, showing some really cool information about like what's in the documents or like which entities tend to be mentioned together, or all that kind of like interesting natural language processing stuff. And that's all additional models that consume this as input.
Is that the reason that you are leaving gaps in different places like that?
that was one. It also made, there were some queries, like there's obviously many ways to skin the cat, but there's a lot of different ways to do it. But the queries that we tended to be running over and over again worked better if we had it separate. Like you basically didn't have as many edge cases. That was the rationale, but it kind of just depends on the use case. Question?
I guess I wonder, in working with RFPs and stuff like that, if there's that particular terms of art that might occur in other natural language and have special meaning.
Oh yeah.
Just like flipping back to like thinking about WBC guidelines where like must, may, should, all something very specific.
Certainly, and that's like a big argument for taking kind of a rule-based, like simple model approach as opposed to just the biggest model you can get your hands on and asking it the answer. Because yeah, the models are trained on the whole internet. We care a lot about a few specific things that are locked down and have meaning that ChatGPT has no idea about, or maybe ChatGPT did read some regulations, but it also read 10,000 other uses of the word shall and doesn't know that it's special. So yeah, keywords like that, or like specific names of components or technologies or processes, like all of that, we found is better like hand curated as opposed to just letting a big language model just chug it and see what it spits out. Question?
How do you verify this graph compared to the source?
So if we have the luxury of having our big data set, option 2 here, yeah, then it would be simple. You could do like a diff, although diffing graphs is also hard, but you could come up with a statistic and compare it and see how well you did. Right now, we haven't done that because no one will give us enough money to do it because it would take a long time. But what we can do is validate the actual use case. So we can create training data pretty easily, like using the linear text, and then see how our model did on it compared to like the other linear models. And then we can say, hey, we're confirming it's working for this use case. In the middle, are they perfect discourse graphs? No, actually, we could find examples of ones that are like horribly mangled or whatever. But as long as the results are still better, then that's okay. And it's all statistical, right? So nobody's perfect, especially not, if you gave an engineer 100 pages of a document, they're not going to be perfect either, like not even close. They're going to fall asleep halfway through. All right, any other questions? I feel like we're definitely over time. Oh, okay. All right, thank you, everybody.